All right. Hey, everyone. So we're going to get started pretty soon. We'll start right on the hour. And so today is going to be the second of 4 videos to cover the entire theory class. So we did regular languages a few days ago, and you can watch that video. It's one of the most recent ones on the channel. We're doing this one today. A week from today, we're going to do Turing machines and decidability, and I may do the fourth piece a week later, but it may be pushed a week after that. But it just depends on what happens between now and then. But the 15th and the 22nd are pretty much guaranteed. Let me just check again. Yeah, the 15th and 22nd are all good. So today we're going to be talking about context-free languages in its entirety. Um, in fact, we're going to talk about something I've not done on the channel yet, and you'll see what that'll be at the very end. But yeah, we're going to be talking about everything about context-free languages. So if you have any questions, just put them over into the chat. I'm watching it right now. Okay, so Albert already has a question. In the PDA to CFG conversion, when we split it into 2 transitions, if we don't introduce a new symbol and use those already in the stack, we cause more matched transitions. Yeah, that's entirely possible. Yep, that's definitely true. So it's just kind of like a trade-off. If you use more symbols, then you have less work to do to make the PDA, but you have to do the additional work of adding some transitions on that final state to pop any possible time when that new symbol's there. So it's a little bit of a trade-off. It's usually a when to use a new symbol though, because you don't have any of those matched transitions at a later point. That is true. Yeah, if any of you have questions, feel free to just put them in the chat. I'm always watching. Again, we're starting right on the hour, so like in 13 minutes or so. And then we'll be talking all about context-free languages and all of their amazingness. Let me just check analytics just to make sure everything is live. It looks like it is, just to be sure though. And please share this video with all of your friends who are taking this class if they have any issues with context-free languages, especially some things like the pumping lemma or any of the conversions. Send them to this video right now, so, or I guess after the stream goes if they can't make it in time. Yeah, so hope everyone's doing well, and we're gonna learn us some context-free languages today. I'm getting a decent chunk of views on the regular live stream that we did a few days ago, which is pretty nice. So it'd be really nice to have the entire course in 4 videos only. And so like if you want to learn theory, you can just watch 4 videos, although it may take, I don't know, 15 hours or whatever, but it'd be nice to have them all in one place instead of one giant playlist of literally hundreds of videos, which is what I have. I think showing a complete solution is valuable. Yeah, I agree. Yeah, one of the issues that a lot of students have is being able to start solving a problem. Once they get started, it's really easy, but it's once it's getting started. So showing not only just the start, but everything in the middle is a win in my book. Yeah, I agree. Yeah, but it'd be really nice to have all the theory content just really condensed into 4 videos, to not have to split things, not to have many videos where they may have to skip a few and they may miss something that they needed at a later point because this class is so cumulative. So having everything in 4 videos is really cool. I should check how many videos do I have in the gigantic theory playlist. Where is it? Oh, I have 120 videos. Oh my god, in the theory playlist, which is awesome. How do you derive 0, 1, 1 without making all rules? Can you just make a single rule that does it? You don't need. Are you talking about a grammar in CNF, or you can just make it directly? Give a brief depth of CFLs using a Venn diagram. I'm not sure if that would actually be helpful because the language structure is not the same thing as a class of language structure. So as an example, if you think about like the spectrum of all languages, like empty set being here and sigma star being over here, try to get it on screen. So it's regular on both ends, but there are non-context-free languages in the middle. So it starts regular and ends regular. Whereas if you compare the class of languages called regular languages, then it's contained within, one is contained within the other. All right, I have to answer something quickly. Sorry about that. Do you take any question today? I mean, that's why I'm doing a live stream. Yeah, I do, sure. Yeah, so if you have any particular things, any examples you want to go over, I am all ears and eyes and every other sense. All right. Yeah, 120 videos in the theory playlist is pretty dang cool. I'm rapidly approaching 200 videos total, which is even more cool. Yeah, but having all of these, having all of the theory content in one playlist is really nice. Because instead of just having someone say, "Oh, I don't know what playlist to go to because I have a lot of playlists," I can just say, that playlist, which has everything that you could ever want. And what I did for the regular language video, what I did for the regular language video was I time stamped everything. So if you visit the regular language live stream video, then I have all of the concepts time stamped, so you can go to exactly the thing that you want, which is pretty nice. I mean, without showing explicitly all rules in PDA to CFG, like how we can describe a grammar can derive a string like without showing explicitly all rules in the PDA. Yeah, I know that. I know what you mean. Not explicitly showing all the rules, but I'm not sure how that's relevant to a single grammar deriving a single string. Because the PDA to CFG thing is just a conversion from any PDA. Because what you can do, because if you're only focused on a single string and nothing else, then you can just make a DFA to do it. You don't even need a PDA to do it. You could make a PDA and try to convert it to a CFG, but I'm not sure how relevant that would even be. But because I'm going to do an example of the conversion, and you can actually see when the important parts are going to be made in the CFG. So there are a lot of rules and variables that are going to be completely useless, but we'll see ones where it actually does make a difference and they're actually important. Okay, how are we doing on, and another thing is that we're going to take a few breaks in the middle so that I don't break my back sitting in this chair for a few hours straight. And I don't go hoarse by talking for 4 hours straight. But there are a lot of rules how we can reach those exact rules that help us derive a special string. Oh, okay. So you're saying like, if we do the conversion, what are the rules that will actually be used in deriving the string? So in that case, it depends on the PDA that you have to start with. So because there are infinitely many languages that have 0, 1, 1 in them, so you can have like a really simple language or a really complicated one, and seeing the path, quote unquote, in making the 0, 1, 1 thing, it really depends on what the PDA actually generating it has. So then, so it might be really easy to see how to actually make that string, but it also might be really complicated. So for example, if you consider the language 0 star 1 star, so like zeros followed by ones, then this string can be made in it. But if you consider the language of zeros followed by ones, where there are more ones than zeros, then that's a more complicated language because it's a context-free language that's not regular. So so it might be a little more difficult to actually see how it's being made. And if you have a lot of symmetry in the language in terms of the rules, and I've done some examples on the channel before where it actually might be really complicated to see, but it just really depends on the PDA that you have to start with. Yeah, awesome idea for a video. Let me make sure I'm centered. I continually move. I wish my desktop could swivel to keep me in focus, but apparently rotating computer screens is just like a dream, a technology dream at this point. It's not a reality. Awesome idea for video would be like an exam study guide for a theory course with examples. So that's this playlist that this video is going in. So it'll be 4 videos, which is a crash course in everything that the theory course has, from start to finish. There was a joke video that I did on April Fool's Day this year when I rickrolled everyone, but and I call that an exam study guide. But the thing is, I can't really do one unless I do one for the entire class, entire course. And the reason is that the strategies for attacking certain problems are different. There isn't like a unifying strategy other than looking at the definitions and using definitions, because those are your friend. I mean, I'd have to think about it. Maybe it's a good idea, but I'll have to think about it. All right, we're gonna get started in like 1 minute or so. So I made an announcement that I'm starting tutoring sessions, one-on-one tutoring sessions. So check out the Discord server. I posted all info relevant to it, as well as on the community tab in this channel. So if you go to this channel, click the community tab, there's a post that I made about tutoring services. So if you want that, then that's great. We can organize it. But if you just want to mooch off my videos, I'm kidding, then just keep watching. All right, using the definitions, my prof says that a ton. Yeah, and that's why I say it too, because I'm a prof too. All right. Okay. Wish me luck. All right. Let's get started. All right, so let's get started. So we're going to be talking about context-free languages in its entirety today. So we recently did a live stream on regular languages a few days ago. We're going to be doing one today entirely on the context-free languages. So where does this context-free thing come from? So the main object that we consider here are something called grammars. So it's not a object that we have really seen before, unless you have watched my videos on regular grammars, which I'm not going to do here, but or I may mention it very briefly. So what a grammar is a language that tells you how to make. Sorry, it's a structure that allows you to figure out how to actually make strings. So actually, let me do it this way. So the main objects that we've been dealing with are machine models, which which compute whether to accept a string or not. So that's the main advantage of a machine model. You compute it by going into states or whatever, and then you accept or not accept. Then we did something called a regular expression. And what the advantage of that is a formal description of a language. Formal description of a language. And what a grammar is a way to figure out formally how to actually create strings that are in the language. So how to create strings in the language. Okay, so different perspectives on how to actually compute with things. So we've done machine models, which is, it's computing whether to accept a string or not by going into states or whatever. Regular expressions are just ways of describing a language in a formal way instead of using something like English. And grammars are ways to see how to actually create the strings that are in a language. Okay, so what we're going to be talking about here are context-free grammars. And I'll give a name. I'll tell you what the context-free means in a sec. So there are 4 things that are in any grammar, whether or not it's context-free. So the 4 aspects of any grammar whatsoever are the first one being variables, second one being terminals. Actually, I should say that variables are sometimes called non-terminals. So if your instructor or something uses non-terminals, that's what this is referring to. I'm used to using the word variable, so that's what I'm just going to use. You could call terminals non-variables, but that doesn't really make sense in this context. Terminals, rules, and a start variable. And the thing that's important about grammars are the rules. So depending on what rules are allowed tells you how the strings are made. So what the purpose of a grammar is to repeatedly apply rules until you get a string. And so the languages here are over languages are over alphabets, and that's what the terminals are. So the terminals are the characters in the alphabet. Think of it like an input alphabet, but since grammars don't really have inputs, it doesn't really make sense to say input alphabet because they don't have inputs. So here, terminals just represent the strings of the language that correspond to a grammar. And a variable is just an auxiliary tool to both start doing the computing or whatever it is, and maybe to do some assistance along the way. So kind of like how states in a DFA are helping you do the computation along the way. Okay, so we got variables, which are just auxiliary tools. Terminals are the strings that we want to make at the end of the day, just like how we want to accept a string in a DFA. The string there, the alphabet for it, is the same as what a terminal is here. The rules are just ways of doing some kind of computation, kind of like doing a transition. And they're very close to a transition, analogously. And the start variable is where you start the work. All right, so as I said, the rules are where the important stuff happens. So the idea is that we have some string of some kind, maybe terminals, maybe variables, or something completely different. And we have something that looks like this. And both of these on both sides are some mix of variables, which I'm going to abbreviate vars, and terminals. Okay, so it's just some mix on both sides. And context-free grammars have, the ones that we're talking about, will have a certain structure, but in general, for grammars, they could have anything on the left and anything on the right. So how does the computation actually happen? What happens is, whenever we see an alpha at any time, if this is a rule right here, if this is a rule, anytime we see an alpha, I could cross that alpha out, that whole string, I can delete it and replace it in the same place with whatever the right-hand side is here. So if for example, if I have 0, 1, 1, replace and then arrow with 2, 3, or something like that, then anytime, and I'll depict it this way. So anytime we see a 0, 1, 1 in something that we're working on right now, something that we're computing, then I can replace this. And so what it looks like, I'm going to cross it out. The 0, 1, 1 is crossed out. And what happens is the rest of it is unchanged, and the 0, 1, 1 is replaced with the right-hand side of this rule if I choose to apply this rule. There could be other rules I could apply, so it's not necessarily there's only one that we can do. Okay, so that's essentially what a grammar is. So what is a context-free grammar? Oh, by the way, variables and terminals, still a finite set in all cases. So if they were infinite, then we could pretty much do anything at this point. But they're all finite, just like with DFAs. But so a context-free grammar, what is its property is that all rules are of the form capital A goes to X, where the A here is a single variable, no terminal at all, and the X over here is any mix of variables and terminals. So the right-hand side can be anything, but the left-hand side has to be a single variable, no terminals, and so a single variable can't be two variables, has to be exactly one variable. So the consequence of this is that whenever a terminal is created at any point, it can never be replaced, because anytime you want to replace something, you must replace a single variable with stuff. You can never replace a terminal or any combination involving a terminal with stuff. So I'll write that down. So anytime a terminal is created, it is never replaced, ever. If a variable is made, then it may or may not be replaced. But once a terminal is made, it can never be replaced. So let's do an example of this. So I'm going to do a really simple example, which is this one right here. And you've probably all seen this one because I've done it many times on the channel. This vertical bar right here, it means multiple rules. So this is saying, multiple rules with the same left-hand side variable. Yeah, so I'm going to talk about leftmost and rightmost in a bit. So this is a grammar. So we have the empty string right here. So the 0 and the 1 here, those are going to be the terminals. There's only one variable in this whole thing, which is s. So this is not only a variable, but it's the start one, because there must be a start variable. And let's just start applying rules. So let's say that we have to start with s. So the key here is that we must start with just the start variable and nothing else. So start variable, which is s in this case, then we can apply a rule. So let's say that I apply a rule, and I can either replace this s with nothing, which is the empty string, or I can replace it with this left side. So remember, there's no variable over here. So if I apply this rule right here, then I must immediately stop because there's no other rules I can apply. But let's say apply the left one. So I apply 0s1. So note that the 0 and the 1 are terminals here in this case. So then those two can never ever be replaced. But this s certainly is a variable. I could stop here if I wanted to, but the key is that I want to actually make a string entirely of terminals, which this one isn't because there's a variable here. So I could apply this rule again to this variable s. So I'm going to cross this s out. The 0 and 1 are left intact because they're terminals. And if I apply the first rule yet again, I'm going to have the first 0, so that's still from the first 0, but this s in the middle gets replaced with 0s1. So I'm going to get 0s1 in the middle, and then the 1 at the very end, which I've already had, which of course never got replaced. And then maybe for simplicity, let's say that we're going to replace this s right here with epsilon. We apply the other rule. So this s gets replaced with nothing. So we'll have 0, 0, 1, 1. Okay? So this is just it's a really simple grammar. And I'll give all the definitions that are needed pretty soon. But first, the language of this grammar, you can actually pretty easily figure out, is 0 to the n, 1 to the n, where n is at least 0. And the reasoning for this is, if n is 0, then we can just apply s to epsilon. And because n equaling 0 is just the empty string here. But if we have n bigger than 0, then if you think about it, any string with equal number of zeros and ones at the beginning and the end, if we take off one of the zeros at the beginning and one of the ones at the end, then we're still going to get a string that is in this language because we took off 1, 0 and 1, 1 at the same time. So if we take off a 0 and take off a 1, and assume by induction that the middle piece will have equal number of zeros and ones, then this one will also have equal numbers of zeros and ones, and zeros coming first. So the language of this grammar by induction is this language. Okay, so what can I say about this? So this language is not regular, obviously, because we've we've done it. So this guy is not regular. And one thing that you can prove, but I'm not going to do here, is that all regular languages have a context-free grammar, which is abbreviated CFG. So CFG, context-free grammar. And so I'm not going to prove this. And you can find videos on my channel where I actually did prove this, but I'm not going to prove it here. Okay, so all regular languages have a context-free grammar. So what are some definitions here? So so this right here, when we applied a rule, so this is applying a rule. So this is equivalent to saying yields. So yields means we applied a rule. So the left-hand side yields the right-hand side because we could apply a rule from the first one to get to the second one. And if we think about, green's not the best color, that's a Pink Floyd song. If we think about, let's just say all of this, which is going from the start variable all the way to getting a string full of terminals like this whole thing is called a derivation, which is the same thing as saying apply rules with the start variable, or starting with the start variable to get only terminals. Okay, so because we got only terminals in this case, this is called a derivation. If we stopped at, like, say, this point, or even this point, it would not be a derivation. Okay, so some other cases. So let's say that we have a derivation right here. So we have S applying a rule, and we got some stuff. And then maybe at some point, we're right here, and we have a bunch of variables, let's say A, B, C, etc. And what happens here is that I replace the A with X. Let's just say A to X is a rule. So then after this, I'm going to have X right there with the B here and then the C here, because I can only replace one variable at a time. So if we also make the assumption that in this segment right here, there are no variables. In other words, that A is the furthest forward variable of the entire applying rules process so far. And we repeatedly do this for, so we pick the furthest forward variable and replace it every time. Then we call this a leftmost derivation. So one thing that you can kind of see if you think about it is that every derivation has a leftmost one. And why is that the case? So if you think about it, we are dealing with context-free grammars here. So the only thing that matters for applying a rule or not is replacing one variable with stuff. So if you have a derivation, you were successfully able to apply a rule at each point. So then what happens is, if you want a leftmost version of that derivation, just focus on the leftmost variable. It must have gotten replaced at some point because we're dealing with a derivation, and derivations don't end with variables at the end. So that means every variable got replaced with stuff at some point, and because the only thing that matters is the single variable and nothing around it, context-free, then we could get a leftmost derivation just by we repeatedly consider just the leftmost variable. So we rearrange which of the rules were applied at each point, because each one of them is basically independent of each other in terms of at each point. So like whatever A gets replaced with here, B gets replaced with eventually, C gets replaced with eventually. All of these are independent from each other. So it's not true that all rule applications are independent, but it's that the ones at each given point are independent because it's a context-free grammar. So every derivation has a leftmost derivation, which will actually be kind of important later. Okay, let's see. I have notes. I just want to make sure I'm getting everything right. Okay, so let's do another example of a grammar. So here's an example. So this one's useful for programming languages, and it's called balanced parentheses. So if we have a string here, let's say, of parentheses, if I have the left parenthesis and then the right one, then we call that balanced. So this one's okay. If we have it the other way around, then this one is not balanced. So that means even though they there's a right one and then a left one, and they correspond to each other, they're in the wrong order. So the left one has to be first before the corresponding right one. So if we, for example, have this one right here, actually I'll do it this way. So this one will also be valid because this one gets matched to here, the inner two get matched, and the last two get matched. So this one would also be a balanced set of parentheses. One thing to note is that the order obviously matters, but the number of lefts and rights have to be the same. Because if there was more of the left than the right, then there wasn't a corresponding match for it because they match one-to-one. So we can think of language, let's call it BAL, which is the set of all balanced parentheses. Oops, need a set notation at the end. So if we want to make a grammar for this, and you can actually show that it's not regular, so we need to use something special about the grammar if it is creatable by a context-free grammar. So if we're going to make a grammar for this, the way to think about grammars is that they're very recursive. So try to work on the base cases first, and then do inductive cases later. So the base case here, what is the smallest set of balanced parentheses you can ever have? It's the empty string. It must be balanced because every left matches with the right, even though there are none of them. You could change it to the string has to be non-empty, but I'm just going to consider that as being balanced too. So epsilon. Or let's consider what are the possible things that can happen in inductive cases. Well, one case is where we have a left and a right, and then we have to recurse in the middle. So kind of like this one right here. So this left matches with this right, but there could be anything on the inside. As long as it's balanced on the inside, then this left and right will be balanced. So then here, we just assume by induction that the middle piece must be balanced. So we'll have here, we have left, s, right. But that will kind of look like 0 to the n, 1 to the n, just changed for left and right here. But we'll never get this string if we just leave it like this. Because if we have this and we apply this rule, we can only get these two right here, but we can never get these ones. So the other case is if you have a set of balanced parentheses right here and another one right next to it, then the whole set is balanced because every left in this side gets matched with a right, and everything on this side, every left gets matched with a right, independently of each other. And we can have a whole bunch of these in a row, which is why if we have the rule SS, then if we apply this rule over and over and over again, we're going to get a bunch of S's right here, which correspond to multiple segments like this where we can dive into it. So we have two segments in this case. Are you teaching CFL? You should probably look at the title of the video. Yeah, yeah, I'm teaching CFL, of course. All right, so that's example of a grammar for all balanced parentheses. Try to make a grammar with balanced parentheses and square brackets at the same time. You'll find it to be very difficult. But if you do just balanced parentheses, it's pretty easy. All right, so what are we going to call a context-free language? So that's going to be any language of a context-free grammar, as you might expect. So DFA corresponds to regular language. Context-free language corresponds to a context-free grammar. All right. Okay. So that's nice. And so what I mentioned before is that every regular language can be made by a context-free language. So this tells us that every regular language is a context-free language, and I'm going to abbreviate that as CFL, context-free language. There are so many TLAs in this class, 3-letter acronyms, but it should be pretty apparent. Context-free language. Okay, so what I want to do here is I want to briefly show that here, I want to show that the CFLs, the context-free languages, are closed under the regular operations. And if you don't remember, these are a union, concatenation, and star. Okay, so how do we actually show this? So the only way we know how is if I have a context-free grammar for 2 different languages, could I make a context-free grammar for the union? TLA is also TLA, yeah, I know. So if you have 2 context-free grammars and I form their union, can I make a grammar for the union? So let's see. So let's say that we have 2 languages, L1 and L2 are context-free languages. So can I make a grammar for each of them? And yes, it is, because I assume that they're context-free languages, which means that there are grammars for them. So let's say that L1 has a grammar G1, and L2 has a grammar G2. So these are context-free grammars, which I'm assuming exist. So then what do I do here? So if I want to do the union of the 2, I got to make a grammar for them. So what I do is I'm going to do this. So I'm going to have a variable s make s1 or s2. So remember, the vertical bar means multiple rules. And what is this? So s here is a new variable, new start variable. And S1 and S2 are the original start variables for those 2 grammars. Okay, why does this work? And one thing I should note is that, so we can assume without loss of generality that there are no variables in common between G1 and G2, otherwise this won't work. So we can just rename the variables because the variables don't have anything to do with the terminal strings that are generated. So they're just auxiliary variables. I can just rename them. So why does this get the union? Well, this is the start variable. There's no other rules other than these 2 that involve this new start variable. So then when I go into here, either I choose the S1 variable or I choose the S2. And because there's no terminals being generated here, this actually is a non-deterministic choice. I can choose whether or not to do one of these two. There's not a forced decision here. So that tells us that, one, that context-free grammars are non-deterministic things, and two, that we can get union because we can non-deterministically choose which of these two to use. All right, so that shows that context-free languages are closed under union. What about for concatenation? So concat. So this is L1 concatenated with L2. And it's actually very, very, very similar. So I'll just stick with red. So here we're going to have S making S1 concatenated with S2. And that works because, one, there's no variables in common. And two, whatever string of terminals this thing makes is concatenated with whatever string of terminals this thing makes. And that's the definition of what concatenation is. Take a string from the first piece, and then one from the second, and then you put them together. All right, what about for star? Let's do pink. So for star, that is L1 star. So the way to handle this one is to think about what star is. Star is either it includes the empty string, or inductively, you pick a string out of the language, let's say L1 here, and then you concatenate it with a bunch of copies of L1. So let's just say you pick 100 strings out of L1 that you want to put together. So you pick one of them, and then you solve the problem on picking 99 strings. So you pick one, concatenate it with whatever you can do with the 99 choices of strings that you can pick out of L1. So that's actually the right perspective to have to whenever you're making a grammar for the star of something. So the way you do it is you make the new start variable, and you do the base case inductive case yet again. So the base case is epsilon, because it's in the star of every language, and then or we go into the grammar for L1, you generate a string with it, and then just go back to the beginning and then try again. So I'll have S1 followed by S. And this works mainly because it's kind of like how we did star for NFAs when we had the final state and went back out to the new start state. That's kind of very similar to what we're doing here. So we can go through the machine, the grammar in this case, and we can come back to the beginning and go through again as many times as we want. And this works because the only way to make a string full of terminals, because this, whatever this is, S1's going to make a string of terminals, let's say, but this S is tagging along for the ride. And so whatever happens, right here, this rule does not have all terminals in it. So we can't stop until we come back in and have the S go away. So when we finally apply this rule, it is the only way to actually get a string of terminals and stop the derivation at that point. So, so that is pretty clear that this shows that context-free languages are closed under star, which is pretty nice. Okay, so do you have any questions? I accidentally put normal delay on the live stream, so it might take a while for your responses to come in if you have questions. I'm gonna continue anyway, but I'm going to see the questions and I'll answer them anyway if they come later. Because I didn't plan correctly. Okay, so one of the annoying things about context-free grammars, okay, so I recently tried to make an exercise, but I can't. Could you try a CFL that it's a non-odd, I guess, odd length string, and that has the same number at the start, middle, and end of what though? Same number of what? Because that actually could make it not context-free depending on what the same number of actually means. Oh, what about complement? We're going to hit that later. because the answer is very different from yes, you can. Yeah, so a complement and intersection, by the way, we're going to hit that later too. And the answer there is also very different than yes. All right. Any other questions? So if it's binary, it's an odd, so it's an even length string, I'm guessing, and it has the same number at the start, middle, and end. I don't know what start, middle, and end means. Yeah, I'm not sure what that actually means, but you can go ahead and answer, but I'm going to continue anyway. So the annoying thing about the context-free grammars is we can have something like this. So if I have one variable, I can replace it with one variable and then just keep going in a chain like this, or something like this. And then let's say finally make epsilon. So we have this really, really long chain right here of what I call a useless rule. Right? Because you can say, well, you're going to make the empty string way down here anyway. Why don't you just make it way up here and avoid this long chain here? So that's pretty annoying. And the other annoying thing is that all of these variables turn out to be really completely useless because they didn't make anything of the string, which is pretty annoying. Yeah, and the other annoying thing is that to make the empty string, we have a whole bunch of rules to apply. So if the perspective you should have is that longer strings should take longer to make. So because you can have any right-hand side of any length you want, you could have, say, S going to capital A or a big long string right here. So a long string, but so then this variable S could make this long string directly, but also what can happen is that A could do this long chain that we did before. And then let's say that variable Y makes variable Z and Z makes epsilon. So it could be that we take this really, really long route to make a really short string, and we can have a really short route to make a long string. If you see the strings have not, they do have odd length, or at least in the examples you gave, they have odd length. So it's not non-odd, and have the same number at the start, middle, and end. I still don't know what does the start, middle, and end mean? I still don't know what that actually corresponds to. If you have a formal description of what the language is, then I might be able to help more. Giving examples of some strings doesn't really help because every string belongs to an infinite number of different languages. So just giving a few strings is not indicative of what the language actually is. If you have a formal definition, that'd be really nice. Okay, so this is kind of annoying. So luckily, there is a way of trying to mitigate against this. So it's something called Chomsky Normal Form, CNF. All right, so what is Chomsky Normal Form? So it's a restriction on the rules in a context-free grammar. And what are those restrictions? So the only rules allowed are of the form, and there are only 3 possible types of rules that you can have here, which are having the start variable make the empty string. So that's the only type of rule that you can have making the empty string. no other variable can make the empty string. We can have a single variable making a single terminal and nothing else. So a is a variable, and little a is a single terminal and nothing else. And the other type of rule is a going to be C. And what are B and C? Oops. Notability fighting with me. So B and C are variables, and B and C are not the start variable. Okay, so A on the left side could be the start variable, but it's yeah. So A is at the beginning. Sorry, it could be any variable, but B and C can't be the start variable. And the consequence of this is that if A is not the start variable, it can't make the empty string, because if we apply this rule, the little a is not the empty string, obviously. And if we apply this one, these two are not the start variable, and the start variable is the only way to make the empty string. And so if you have any variable other than the start variable, it must make something of the string. All right, so Gene's question was, W is odd length and has the same symbol at the beginning, end, and center. Okay, so let's do this. All right, I don't know why Notability crashed. That was not good. Okay, so I'm going to answer Gene's question briefly. Move this to a new page. So then, if we have the example language that Gene gave, which is all the strings in 0, 1, star. Yeah, this is 0, 1, star. The length of W is odd. And although that won't actually matter in this case. And has the same symbol, so same symbol in the beginning. I'm actually going to write it a different way. So, and the first symbol equals the middle one equals the end one. Okay, so the rest of the string just does not matter whatsoever. As long as the beginning, the middle, and the end are all the same, then we're all good. So again, it's a good idea to think about inductive versus base cases. So what is the smallest string that we can have here? Well, since the length of W being odd, it must have, the smallest string we can have is of length 1. So if we just make the two strings of length 1, that'll cover that immediately. So then now we got to figure out the inductive cases. So the inductive cases is either it starts with the 1 or it starts with the 0. So if it starts with a 1, okay, actually I see what you mean. Yeah, so if it starts with a 1, it must end with a 1 and have a 1 in the middle. Okay, so yeah, so let's think. So if we have a 1 at the beginning, and then at some point later, at the very end, we must have a 1. But we also must have the middle part being a 1. It turns out that I can't do this in this way. I can't just say, I'm going to have a variable a here that makes the rest of the first half, then the 1 in the middle, and then the a again, and then the 1 at the end, to have the characters match. This won't work because these two a's can make strings independently of each other. So what we should do instead is to do a different technique, which is what I call forwarding. So what forwarding is that A is going to focus on making the middle piece of the string, and it could have anything it wants as long as the middle character is a 1. Okay, so the A variable makes all strings of odd length with 1 in the middle. Okay, and this one's actually pretty easy to do. So the way that you do it is on either side of that 1 in the middle, it could be anything, because we don't care what the rest of the string is as long as the middle character is a 1. So what we can do is 0A0 or 1A1 or 0A1 or let's see, or 1A0, and then the final recursive case. Don't know why I'm getting notifications. That's not good. And then if you finish the recursion, because I'm generating the same number of characters on both sides in all of the other rules right here, when we're done, we must be at the middle character. So the 1 must be the thing that we need at the middle. And then the other possibility is that we have a 0 at the beginning, but we must have a 0 at the end. But we can't do the A variable here because that is producing a 1 in the middle. So we need a B variable to do this job. So then what is the B variable going to do? It's going to do exactly the same thing as the A variable here, except now it's going to be B everywhere, and it's going to end with a 0 instead of a 1. So 0 here. And all of these are going to be B's instead. So B, 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 B. Okay. So again, it's focusing on the base case as well as the recursive case. So the base case here was these 2 small strings. Actually, we kind of did it twice. So a base case being here of the overall string, and then the inductive cases, well, it either ends with and starts with a 1 or ends and starts with a 0. And we had to have this differently because the behavior of the middle piece of the string is different. So we needed 2 different variables to handle that job. You may be able to squash this a little bit, but then we thought about, well, what about the middle piece of the string? Well, the base case is we're at the middle character, and in the inductive case is, well, we're somewhere else, and we got to make in an odd length string, so we got to chop off an even number of pieces every time because the middle piece has exactly 1 character. And so since the A and B variables must make an odd length string, each of the other rules must make an even number of characters, even number of terminals, I should say. Okay, so that's that one. So let's talk about Chomsky Normal Form. So one thing that we noticed when I was talking about it was that no non-start variable can make the empty string. It's just impossible because the only variable that can make it is the start one. So what we're going to actually show here is that every CFG can be converted into CNF. Okay, and why would you want such a thing? So there are actually several reasons. Well, one of them being this, because every variable is productive in a sense, in that they actually make something versus just going to make epsilon and not be productive at all. Another reason is when we're going to use the pumping lemma later, it helps prove that. Another one is to figure out, so determine how many rules to apply to get a string, because it could be that we can have arbitrarily many rules to apply to make a string, like the empty string we saw earlier. But here you can actually determine the exact number of rules to apply, which is nice. It doesn't tell you necessarily which rules to apply, and that'll be the job of an algorithm we're not covering today, but it's the algorithm called the CYK algorithm. So if you've ever heard of this algorithm, and I've done it on the channel before, it heavily uses the structure of grammars in CNF. So CNF has a lot of nice applications. So the fact that we can convert any context-free grammar into CNF is really cool. So let's just do a grammar in particular. So I've done on the channel the full proof of this theorem and in an example, but for the interest of time and our sanity, I'm just going to do an example in tandem with the explanation. So let's do the balanced parentheses example. So we have S going to epsilon or left S right or SS. So this is the grammar. Let's say we want to convert it into CNF. So it's kind of there, not quite, because this is not the best example. So what I'm going to do is I'm going to cut and paste the example we just did, and maybe hopefully I don't go insane doing this one example. So I'm going to copy this guy down. Paste. Okay, so we got this grammar right here. And then maybe I want to do the star of this example. So I'm going to attach onto it, so I'm going to call this S1. Just like when we did the star closure property, I'm going to tack on this rule at the beginning. Okay, so I'm just going to tack that onto the beginning. It's not the same language as before, but it's just an example because I want to do an example of conversion. Okay, so what are we going to do here? Well, this grammar is not in CNF. Why? Because we have mixes of variables and terminals here. We have the start variable appearing on the right-hand side of some rule, namely this one. And I think those are the only issues. Yeah, so maybe let's make this more interesting. So I'm gonna make this a little bit more interesting. Okay, so I'm gonna tack on these rules. So this grammar is again not in CNF because we have a non-start variable making the empty string, and we have right-hand sides that have a single variable. So we can have exactly two variables or exactly one terminal, but nothing else other than S making the empty string, which is okay. So the way that we convert this is with a 5-stage conversion. So the first step is to ensure the start variable not on right-hand side, which it clearly is in this case because there is a start variable here. So what I'm going to do is I'm just going to literally copy and paste this grammar down. I'm going to paste it down here. And the way that we'll fix this is that I'm going to add a new start variable I'm going to call S0, which is going to go to the original one. So this guy right here is the new start. So new start variable. And one thing that we want to make sure of is if we want to make sure that every grammar can be converted, then I got to make sure that I don't change the language of whatever the grammar had before. So this change right here doesn't change the language in terms of the terminal strings that it can actually make, because whatever the derivation was from this start variable coming down, then I can just tack on S0 at the beginning, and that will give me a derivation in this guy, and vice versa. So if I have a derivation in this big boy, how do I get a derivation in the original? Well, this one must start with S0, so I can just take away the S0 start thing at the beginning, and I must start with the original start variable, which is all that I need. Cool. And so the language doesn't change as a result. Okay, so the second step here is to quote-unquote eliminate rules that involve epsilon, which I'm going to call epsilon rules. So it's not literally delete them, but it's to handle them strategically, which means that yeah. So strategically means that we gotta be able to simulate these rules. So like S1 can't make epsilon directly, but if I make it indirectly, that's a good thing. So if I don't have a non-start variable making the empty string at some point, then that's a good thing. So here's what we're going to do. So I'm going to copy and paste this grammar again. I know it's a big boy grammar, and it's going to get a lot bigger, trust me. So I'm going to try to make it easier to see once we do more of this. Okay, so what I'm going to do is I'm going to create a list, which is going to call, I'm going to call the nullable variables list. And these are the variables that could either directly make epsilon or do it indirectly. So the ones that can make it directly are the S variable and S1 right here. So those are the ones that can make it directly. But also S0 could make it indirectly because we found out that S can make it. And so this rule tells us that S0 could also make the empty string. But we can see here that A can't make the empty string because there's no right-hand side. Actually, both of these variables have terminals on the right side. And so therefore that tells us that A and B are not on this list. So what do you do once you have this list? What you do is you copy and paste rules around. So what we do first is to make sure that the S0 does get epsilon because it can make the empty string, and we gotta make it at some point. And the only way we can do that is with the start variable. But with the S1 being nullable, first off, we need to delete this one because we can't have a non-start variable making epsilon. And there is an automated way of doing this, by the way, but I'm not going to talk about it here. So if S can make the empty string, which it can, then in this rule right here, this S could make epsilon, and S1 might make something else. So I'm going to add a rule. Actually, I'll stay pink here. So I'm going to add the rule S1, only S1, because this S could theoretically make epsilon. So we're doing it indirectly versus directly. It could be that S1, because it's on this list, S1 makes nothing, and it makes the empty string, and S makes something. So I gotta add the rule goes to S. We'll deal with this in a second. But it could be that both of these make epsilon because they're both on this list. So I could, if I wanted to, add a rule that said or epsilon because that corresponds to when both of these are empty, but I don't want to reintroduce epsilon rules. Okay. What about down here? Well, this epsilon rule right here needs to go eventually. So the S1 variable, there's none of these rules corresponding to S1 are on this list on the right-hand side, so we don't need to do anything. The A and B variables, we don't need to do anything. And I think that's it. So this was a pretty easy change. The only thing that's wrong is this rule. So if we have S making itself, that is a completely useless rule. So we could delete it. S going to S1, that's not useless. But S going to itself and nothing else, that's just adding a rule for no reason. It doesn't do anything for us. Okay, so that was a pretty easy change. And if I make a mistake, just put it in the chat, I'm watching. Okay, so the third step here, step 3, is to eliminate what are called unit rules. So a unit rule, in this context, is a variable that makes one variable and nothing else at all. It could be itself, or it could be a completely different variable. So we actually have several instances of this. So we have this S right here on the right side, S1 here, and the A and B over here actually. So, so how do we actually handle this? I'm going to copy and paste just like before. So paste. So what do we actually do here? So what we're going to do is we're just going to copy and paste rules around. So, yeah, so what are we going to actually do? So this A, what we're going to do is we're going to replace it with all of the right-hand side of A. And actually going to do the same thing with B too. So the thing is that I could just copy and paste all of these rules up here, but it'd be completely unnecessary. So this is not the original language, obviously, because I added new rules to demonstrate points, but I'm just going to copy and paste them. There's no point in pasting a rule that you already have. So you could, if you wanted to, have duplicate rules, but there's just no need. It doesn't do anything for you. So I'm just going to copy and paste all of the rules. We already have, actually I'm just going to check them off. So we have this one already, this one already, this one, and this one already. But it's just all of these ones that I haven't done yet. So, okay, yeah. So what are we going to actually do here? Okay, we're going to have the 0A01. We're going to have the 0A11, 1A0, or 1B1, or 0B1, or 1B0. And then I can get rid of the check marks. Okay, so that was pretty easy. What about this S1 unit rule right here? I'm not going to copy and paste all of those. What I'm going to do is a little technique I like to do, which is to put a little quotation mark right there and to say all of this stuff right here, that belongs there. So again, it's just copying and pasting rules around. And for this S right here, which was a unit rule, I'm going to do the same thing. So, although this will get a little messy. Okay, so what goes here is whatever the right-hand side of S is, because it was a unit rule, and whatever was right here is the right-hand side of this S1 variable. Okay, again, so these steps 2 and 3, these are usually the hardest steps, but it really is just copying and pasting rules around. Okay, you're not doing anything new. Actually, for step 2, you got to do a little bit more to look at when a variable can make epsilon or not. But step 3 is just copying and pasting rules around, and then deleting the unit rules because we can't have those. Okay, so then what is step 4 of 5? So some textbooks put this into 4 steps. I like to split the last one into 2 steps because it's usually a lot of work to do it in 1, but it's nice to do it in 2. So here we're going to ensure the right-hand side. I'm surprised there are no drop frames this entire time, which is pretty cool. So ensure the right-hand side is only variables or one terminal. Okay, so it's not 2 variables on the right side, but it's just only variables or one terminal. So the one terminal is the second type of rule that we're allowed to have. It's just that we could have really, really long right-hand sides, potentially. So I'm going to copy and paste this monster of a grammar here and prepare for it to get larger. So what are we going to do here? Well, what we're going to do is we're going to strategically change these terminals right here that involve a mix like this. We're going to change them to variables. And the way that I do it, when I do this in my spare time, obviously, is I'm going to make 2 variables, u0, which is going to only make 0 and nothing else, and then a variable u1, which is only going to make 1 and nothing else. Okay. Based on one of the comments before, how would a CFL be? So 0 to the n, 1 to the m with m less than 2 to the n. So here's my advice. I'm not going to do it myself. The advice that I have is do it where m is less than or equal to 2n. That might help. All right, so what about this? So the way that we do this is we're not going to replace the single terminals right here because those would reintroduce unit rules, and I don't want to do that. I'm going to replace all of the 1s and the 0s. Oops, I should not delete all of them. I'm going to use a certain color. Let's use white. So 1 in both cases here. So U1, U1. This one's going to be U0 in both cases. This one's going to be 0 in both cases. 0, 1. This may be the most labor-intensive one of all. So this was 1, 0. This one's going to be 1, 1. This one's going to be 0, 1. 1, 0. Yeah, it's all on screen. So 0, 0 in both of these. One in both cases of both of these. So U1, 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 U1. We won. So 0, 1 in both cases in this one. So U0, U1, U0, U1. And then, of course, 1, 0 in both cases here. So U1, U0, U1, U0. And I assume that these are going to be copied and pasted upstairs here. So that shows us that, and this step doesn't change the language of the grammar because it's just an indirect route to make the terminal that would have already been made there in the first place, which is exactly what we want. Okay, so then now the only problem that's left, which is step 5, is to break up, quote unquote, long right-hand sides. Okay, so what long means here is that we have 3 or more variables on the right side. So this one's actually pretty easy to do. Once I copy and paste this big boy. So I'm going to paste it here. So the way that you do this is, so the only rules that are kind of troublesome are these ones in the middle right here. This S1S is okay because it has exactly 2 variables. So the way that you do this is you will pick 2 variables out of, say, this triplet right here. So I'm going to pick those 2. I'm going to delete them. And I'm going to insert a brand new variable I'm going to call Y1. Nothing to do with the U1 there, but it's just a new variable I call Y1. So Y1 is going to make what was there originally, which was U1 A, I think. Yeah, U1A. I'll make sure that that 1 looks better. And then, so anytime I see a U1A anywhere, I'm going to replace it with a Y1. So U1A, so that's going to be a Y1. U1A, that gets replaced here. And if you have a longer right-hand side, then you will have to do this step repeatedly until you whittle down the right-hand side to exactly 2 variables. So then, are there any U1As left? Nope, I don't think so. So then let's move on to the next one, U0B. So Y2 is going to be U0B. So anytime I see a U0B, I'm going to replace it with Y2 in a context where there are 3 or more variables. If it's just those 2, then I'm not going to do anything. It's just when I have 3 or more variables will I replace it. Okay, so then this one becomes y2 u0b. So these two get replaced. So y2, y2, u0b. I don't see any others. So then I think we'll only have 4 y variables, so to speak. So then the third one will be a y3 going to u0a. So anytime I see a u0a in a context of 3 variables, I'm going to replace. So these two are going to get replaced, y3. And then these two get replaced. So y3, y3. Yeah, it's a lot of replacements. Yeah, I agree. So then the final one will be y4 making u1b. And so that one gets replaced there with y4. And this one gets replaced. And then this one gets replaced. And I think that's it. Oh, there's one I missed. It's that one. Y4. I think I got them all. If you see one, just tell me. But this works. This doesn't change the language because even though we're going through this indirect route with this other variable, we're still going to eventually produce the same right-hand side we had before, and thus we haven't changed the language, which is pretty nice. Okay, so this process can actually work with any grammar at all. So we didn't really rely on the properties of this grammar in particular, because I added rules. I have no idea what the language of it is. So it turns out that this works with any context-free grammar. So what we get at the end of the day is that every CFG can be converted into Chomsky Normal Form, CNF. All right, so what I'm going to do is I'm going to take a short break here, and then we'll come back and start talking about other stuff like PDAs and lots of things related to those. So I will see you all in a while. Okay, so let's get back into the swing of things. Let's make sure I have my notes ready. Where are my notes? Okay, so we just showed that we can convert any grammar into Chomsky Normal Form. And then I now want to talk about a machine model for the context-free languages. And I'm going to skip the motivation on how this model's created, but I'm just going to jump straight to the point, I guess. So these things are called pushdown automata. So they're abbreviated PDA. And what it is the same as an NFA, in what it can do at least, but allows for a stack and operations on the stack. And what are those operations? So what are these operations? What we're going to allow you to do is we can allow you to push or not onto the stack and pop or not on the stack. Okay. One thing to keep in mind is that the pop has to happen first. So if you try to push something, if you want to push and pop something, which kind of just means change the top symbol on the stack, you have to pop first. Because if you try to push first, because of how the stack works, the thing you push is on the top, but the thing you want to pop is not on the top of the stack anymore. So you have to pop first. So the way that the transitions work is that, let's just say we're going from state Q to Q prime. Then every transition is going to look like this. So it's going to be A, comma, X goes to Y. And what does this actually refer to? So this part right here is what we read or not. So it could be epsilon or a single character, just like before. So the X here is what we pop or not. And the Y here is what we push or not. So that's all fine and dandy. So one thing that you might wonder is what happens if we try to pop an empty stack? You can always push onto a stack because it can grow arbitrarily big. But if you try to pop, it may not have anything on it. And so what happens then? So the computation stops if we try to pop an empty stack. The technical term for this, believe it or not, is the PDA hangs itself. Not the lightest terminology of all time, but the PDA hangs because it can't go anywhere. Okay, and we can have any number of transitions of any type, just like an NFA does. So the way to figure out whether we can do this transition or not is we can do this transition if we can read the A or not, and we can pop that character X or not. If there's no pop or read, we can always do that transition. But it's just if we have to read something, and if there's something to pop, then we may or may not be able to do it. So what is the condition on accepting? So we accept if if we're in a final state. So we still have states and final states and start states and whatnot. The only thing that changes are the transitions. We accept 2 if we've read all the input. So these first 2 are exactly the same as with an NFA. But here, the consequence of this is that we don't, in fact, require the stack to be empty. Okay, we don't require the stack to be empty when it accepts. However, the stack, let's do it this way. So the stack will always start empty. And there's some models in some textbooks I've seen where there's a certain character that's placed on the stack at the very beginning. It turns out that we could modify the model where we can always assume that, but I'm just going to make the assumption that the stacks always start empty, always. So what we want to do is we want to show that this is the right model for context-free languages. So how do we actually do that? Yeah, so how do we do that? So let's do an example right here. So let's do 0 to the n, 1 to the n, where n is at least 0. So we made a grammar for this. And so if these are the right model, we better be able to make a PDA for this language. So since this language is not regular, we have to use the stack in some way, some non-trivial way. Well, because we have the same number of zeros and ones here, the ideal way of doing this is whenever we see a 0, we put it onto the stack, and whenever we see a 1, we match it with a corresponding 0. So that's the basic idea. So the way that we'll do this, and we'll see why we do it this way, is I'm going to put a bottom of stack marker on the bottom. And the reason for this is that we don't want to ever pop an empty stack. So here, I'm not going to read anything. I'm not going to pop anything, but I'm going to push a $, which is a special symbol. It's just some symbol that I made up. So the things I can put on the stack could be anything that I want to. It doesn't have to be on the input or whatever. I can put whatever I want on the stack because we're only reading the strings. We care about the strings that we're reading, not things that we put onto the stack. But we can put anything we want on the stack. So here in Q1, what I'm going to do is I'm going to, whenever I see a 0, because that's the thing being read, I'm not going to pop anything, and I'm going to push a 0 onto the stack. So I'm trying to match them up. Decision problems for CFLs, that's going to be covered in the next 2 live streams. This is entirely only about context-free languages. Whenever I get to decision problems, those are going to be in the decidability and undecidability live streams we're doing in the next few weeks. Okay, so if stack does not have to be empty, more zeros than ones would have to be accepted without a sentinel. I'm not sure what that means. Maybe you can clarify. So what I'm actually going to do here is something that I'm going to call a triple epsilon transition. And the reason for this is we need to accept the empty string at some point. And if I have this involving a read here, then that's not going to allow us to accept the empty string. So here I'm going to go down to a state Q2, and it's going to read a 1, but pop off a corresponding 0 that's on the stack. And it's not going to push anything because I don't want to undo the work that I just did in popping that 0. So why is this good? It's good because if we put zeros on the stack by doing this, non-deterministically come down here, because these things are non-deterministic, just like context-free grammars are. Then when we come down here, whenever I see a 1, I better match them with the corresponding 0, which is what I'm doing here. And if everything matches up, then there must be nothing on the stack other than that $ symbol. So then what I'm going to do is I'm going to come over here by popping off the $ symbol. The only way I can take this transition is if I see a $ on the top of the stack. And then here I'm going to go to an accept state. Okay, and this works because I could theoretically come here without reading the whole string in case of where I have more zeros than ones. The thing is, because if I have more ones than zeros, then I'm going to match all the ones with the zeros and still have ones left on the input. Then if I come over here, I don't read anything, but I haven't accepted the whole string. I haven't read the whole string, and so therefore I can't accept. Okay. So, and the other reason, if I have more zeros than ones, then I can't even I can't even do some of these transitions down here. So it's no issue. Okay, so this is a little PDA for this context-free language, but we want to be able to show it in general. So what we're going to show here is that every CFG can be converted into an equivalent PDA. Okay, so how am I going to actually do this? How are we going to actually do this? So the idea, which I'm going to write down, is to simulate the derivation. So simulation, God, I wrote that terribly. Simulate the derivation on the stack itself. Yeah, guys, I'm going to do decidability problems next in the next live streams. Not today. I will do them, but not today. Okay, so simulate the derivation on the stack. Then let's say that we have a derivation right here so far is going to be, let's say, x1, x2, up to xn, where the xi can be a variable or a terminal. Okay, it could be either one of those two things because it's just a derivation so far. Well, the way that we're going to do this is we're going to make a little transformation into the stack right here. So here's the stack. And what we're going to do is we're going to have xn here, and then it's going to work its way up to x2 and x1. So that's going to be the transformation that we want to do in the PDA. Why does this make sense? Because the derivation is read from left to right. And so the stack works from top to bottom. That's how we access things in the stack. So if I want to, say, apply a rule with, let's say x1's a variable, then if I want to apply a rule, well, that's really easy because I can pop off this x1 here, and I can replace this x1 on the stack with the contents of what the rule is. We'll have to deal with that in a second, though. But if x1's a terminal, remember terminals are never changed at any point. So if x1's a terminal, the thing on the top of the stack is a terminal, and what we do is we match them up with the corresponding input. Remember, PDAs get input. So if we're making the so-called string on the stack, we got to be able to match it up with the input directly. And so if x1's a terminal, and it's on the top of the stack like this, then we just match it up with the input. And if it's a variable, we apply a rule corresponding to it. We'll see how to actually do that when we do an example. Okay, so let's do the 0 to the n, 1 to the n grammar example. So here's an example. S going to 0, S, 1, or empty. So that's the grammar I want to make a PDA for. Okay, so the way that we're going to do this is I'm going to have what I call base states. And so this is how this is going to work. So I'm going to have a start state here, and I'm going to push on, just like before, a special symbol, which is going to be $sign here, which is, so here I'm going to go to a state Q1, and then here's where the magic starts. So remember, every single derivation, since we're simulating it on the stack, must start with the start variable, no matter what. That's how every derivation starts. So if we want to simulate it on the stack, then we need to put the start variable on the stack. And so that's what we're going to do here. So we're not going to read anything, and we're going to push the start variable, which is s in this case, onto the stack. And then here, I'm going to go to a state I'm going to call QLoop. And the purpose of this state is if we see a variable on top of the stack, we'll apply a rule. And if I see a terminal, I'll match it up with the input. So in this case, there are two terminals in this grammar, which are 0 and 1. So I'm going to have two self loops right here. One if we see a 0 on the stack, and one in the other case if we see a 1. So if we see a 0 on the stack, I want to match it up with the input directly. So if I see a 0 on the stack, I want to read a 0 at the same time because I want to match them up 1 for 1. And then it's similar for the 1 terminal. Okay. What if we want to apply a rule though? So let's say like this s goes to epsilon 1. Actually, what I'm going to do is I'm going to give myself some more room here. And I'm going to move this rule, this transition down. So let's say we want to do this s to epsilon rule. So that says we're seeing a s on the stack right now. Well, I shouldn't read anything because the purpose of reading is when we see a terminal on the top of the stack. We don't have a terminal on top of the stack now. So what we're going to do is we're going to not read when we're doing when we're trying to apply a rule here. And the way that we're going to handle this is we're going to not read anything, and we're going to pop that s off, because the only way to know which variable to use is to actually pop it off. And then we're going to push onto the stack the corresponding right-hand side of that rule. So it's going to be s going to epsilon, because in this case, I'm pushing the right-hand side of this rule, but it's nothing. So I don't need to do anything special here. There is something I need to do here, but not for this one. So this is another self loop I'm going to add here. But for this one, this is a little different. So I need to have some kind of way of popping this s off and pushing this right-hand side on. The problem is I can only push one character at a time. So we got to figure out which characters should I put onto the stack. The thing is, remember that the top of the stack is corresponding to the left side of the derivation. So the thing I want to appear at the top of the stack should be the leftmost thing here, which is the 0. So the first thing I should push on, in this case then, is the 1. And then we push on the right-hand side in reverse order, purely because we need the left side of this part right here to appear at the top. So the last thing we put on should be at the top, which is the 0. So since I can only push one thing at a time, I'm going to break it up into multiple transitions, 3 in this case. So the way that I do this, because this is called Q loop, is to do a bunch of, in this case only one, loops, a set of transitions that form a loop that go back to Q loop. So here it's going to not read, so these transitions don't read either. I'm going to pop the s off to know that I can actually apply this rule to start with. Then I'm going to push the right-hand side in reverse order. So I'm going to start with the 1 here. Then I'm going to go to a state, I'm not going to name it. And then we push this 1. Now the next thing we need to do is push the s on. We can't pop anything because I don't want to undo the work that I did. So here I'm going to push on the s. And then I'm going to come back by pushing on the 0, which is the last thing. So epsilon goes to 0. And then come back. So if we see an s at the top of the stack, either we apply this rule, so to speak, or we apply this part right here, which is going to do the replacement of s with 1s0, with 0 being at the top. And then once everything matches, then there shouldn't really be anything on the stack other than that special symbol. Why? if everything matched up perfectly, then if there was a variable, then we must apply one of these two sets of transitions. Or if it's a terminal on the top, then we apply one of these two. So then everything supposedly matches up. And so what we'll do here is we'll do a check to see if we have popped off, if we have the $sign on the top, then we will proceed to go to an accept state. So here I'm going to pop the $sign off, and I can push whatever. It doesn't matter in this case because I don't have to end with an empty stack. And I go to a final state as a result. Cool. So we didn't rely on any properties of this grammar to be able to do this. You put these 4 base states in, 0, 1, loop, and the final state. And then you have self loops for every terminal in the grammar. So you read it, pop it, and don't push anything. And then you have a series of loops that go out and come back. In this case was only 1. This one was only 1. Where you will pop off the left variable, and then in a series of transitions, push on the right-hand side in reverse order because you want the left side of the rule to appear at the top of the left side of this part to appear at the top. Thanks, Anik, for your kind comment. All right, so that tells us that every CFG can be converted into a PDA. Now, what about of course, the other direction? Now, every single PDA doesn't have this form because, in fact, there may be a transition that reads coming out of the start state. It may not look like this. So what are we going to actually do here? So we're going to show that you can actually do this conversion. So every PDA can be converted into a CFG, an equivalent CFG. So this is actually really hard to try to derive yourself. This one, I suppose that if you thought about it hard enough, you can actually come up with it, because it's just simulating one thing with another. This one is bonkers, but it's actually pretty cool how it works. The idea is we're doing a bunch of recursion in some sense. We're solving smaller subproblems, and then you put the subproblems together. So how do you actually do this? Well, the first thing we need to do is to, actually I'm going to write it this way. So we're going to have a bunch of steps right here. So step 1 is to ensure the PDA has one final state, has exactly one final state. And then step 2 is to ensure every transition either pushes or pops, but not both. So I'm not going to actually do these because I recently did them on the channel, so watch the videos for that. But I want you to actually think, how would you actually do this? These 2 steps I'm very sure you can do if you thought about it for a few minutes. Okay, so these are not difficult to do. Okay, so once we have these 2 steps done, then what do we actually do? So the proof then is based on analysis of stack height. Analysis of the stack height over time. Quote unquote over time. By over time, I mean when we apply more transitions in the PDA. So what actually happens here? So the first step is not as important right now. The second one is important. So if you think about it, every transition changes the stack in some non-trivial way. So because you must do one of the 2 operations at every point. You either push something or you pop something, but you can't do both. So the stack height actually changes by 1 on every single transition. So it either goes up by 1 or it goes down by 1 every single time. So the way that you look at this is you look at what the stack height could actually do over time. So what I'm going to plot on this little, okay, so what I'm going to plot here is on the vertical axis, I'm going to plot the height of the stack over time. This is not any particular example. This is just getting the concept across. And then time is going to be on the horizontal axis, which means the number of transitions that are applied. Well, remember that the stack starts empty, and in order for this PDA to actually do anything, it must actually push something onto the stack. Because if it tries to pop, then the computation stops because the stack's empty. And it can't stay level because the stack must change height at every time. But it could come back down to 0 right here, potentially. But in general, it could go up and down, up and down. It's never flat anywhere, which is key. So it can come down to 0 again, and then maybe back up, and then back down to 0. And then maybe it stops here. So actually, there's one other step that we need to do that I forgot to mention. Sorry, apologies for that. Step 3 is to allow the stack to be empty. And the way to do that, I suppose that you can actually do it yourself, but I'll tell you anyway how to do this step 3, which is to, in that single final state, just put a bunch of transitions that will pop the stack. Okay, and don't read anything and don't push anything. So it's just a bunch of transitions that are epsilon. Something goes to epsilon. So they pop something, but they don't push anything. Okay, so let's actually look at this. So this is what happens over time. And one thing that we can notice here is that if we look at this very first transition that pushes right here, it actually must match this one way down here. Hey, thank you for your videos. Thank you for watching. Once we started covering CFGs, they helped a lot last semester. Cool. So if we think about it, if it doesn't touch 0 at some point in the middle, this pop right here must match this push because it never popped in the middle. So so there should be, these two transitions are what are called matching transitions because they must have the exact same symbol because we allow the stack to actually be emptied. Okay, so then what do we actually do with this? It actually is just a very simple base case induction type argument. So the way that the grammar is created, so what is the CFG going to have? It's going to have variables A sub P Q. So this is just standard notation, where P and Q are states of the PDA. And the interpretation of what A sub PQ does is that it creates all strings going from P to Q with the same stack height. The thing is, for the same stack height thing, we'll get that for free, so we don't actually need to really think about that too much. Thanks, Anik. You're giving me lots of compliments today. Thank you. Okay, so what are we going to actually do here? So the way to handle this is with simple base case analysis. What is the base case in this case? So the base case here is when we have the same state in the two subscripts. So A sub P, P. Well, here what this means is all the strings that go from state P to state P with the same stack height. And there may be some really convoluted route that goes through the PDA and then eventually comes back to with the same stack height. That is totally possible. But we're focused on certain short strings that we can make. What are some short strings we can make here? Well, one short string is in fact the empty string, because if you think about it, if you don't apply any transitions whatsoever, then you're still in the same state that you were before and with the same stack height you were before. And so you didn't actually read anything because you didn't apply any transition. So one way to go from state to itself is to not read anything because you don't do anything. Why is this a base case? Because if you think about that picture with all of the little mountain looking things, if you focus on one mountain right here, so one mountain, and you focus on the very, very top of the mountain, so this part right here, the snow caps, or I guess red caps, so to speak. So if you focus at the very tippy top right there, what happens is the two transitions, the first one ends in the same state that the second one starts in. And so because of that, what happens is you're going to need to be able to transition from going up the mountain to going down the mountain. So you can think of this as the left variable corresponds to going up the mountain, and the second one corresponds to now we're going down the mountain. Okay, so it's base case because the inductive case is lower on the mountain. So then by induction, we just move up and up and up the mountain. At some point, we must meet at the top, at which case this base case will apply. Okay, so then there are actually two possible inductive cases. And in fact, if you were, I just realized this right now, and I'm going to start using it in my teaching, which is actually pretty amazing. Remember the balanced parentheses example. So actually, I'll rewrite it here. So S going to SS, or left S right, or empty. It turns out that the analysis here, whether we go into the within two parentheses or we have two sets of different parentheses, is the same here. I just realized that. It's so awesome. So what are the two inductive cases that can happen? So inductive case one. The first case is we have two mountains, or two sets of mountains at least. So we have two mountains right here where it hits 0 only in one place in the middle, and then it comes back down, and then it hits the 0 at the beginning, middle, and the end. Okay, so this clearly is the same stack height at all three locations. But I could be in any one of the three any state in either one of the three locations. So let's say that it's P here, I'm in state P, and then here is state, I'm going to call Q, and some random state in the middle R. So any one of these could be different or the same. They could be totally random states, but they're just three states. So if I want to solve the big problem, going from P to Q here, so if I want to get from P to Q, then one way of doing that is to traverse this mountain and then traverse this mountain, which means that I'm going to have to find some way of getting from P to R with the same stack height. Well, we know what that is. That's A sub PR. And then some way of getting from R to Q with the same stack height again. So A sub RQ. So this is a rule that you will generate for every single triplet of states. They could be all different, all the same, or anything in between. And this works because assuming by induction that I can get from P to R and from R to Q with the same stack height, then I can get from P to Q with the same stack height. It's kind of like if I can travel from here from point A to point B and from point B to C, then I can, by transitivity, get from A to C. It's the same idea here. Okay, and then what is the other inductive case? Inductive case 2 is instead of having two mountains or more, we have exactly one mountain. Okay, so exactly one mountain. So let's look at that case where we have exactly one mountain. It may go up and down, but it doesn't hit 0 anywhere in between other than at the ends. Okay, so the thing is, let's look at the beginning, the first transition, and then the very last one. Okay, so we know from what we discussed earlier that they must involve the same stack character because it never hits 0 in between. And because it never hit 0 in between, these two must be exactly the same stack character because there's only one mountain to consider. Okay, so let's look at this in more detail. So I'm going to blow this up a little bit. So here we have the push transition occurring, and then the rest of the mountain in between. And then the pop occurred over here. Okay, so what actually happened? So this guy must push something, let's call it X. We don't know necessarily which one it is, but we know it's some symbol. So we know the pop one on the other side must be popping the exact same thing. So this must pop X. Okay, and I could be in any one of the possible states at any one of the points. So let's say that we're in state P here, state Q at the very end, and I don't know what the other two states are, but let's just say they're R and S. They could be totally random states, or all the same or all different, I don't know for sure. And what's red on one of the transitions is going to be, it could be anything in particular. So let's say that we will read an A on this one. It could be epsilon, but let's just say it's an A for sake of convenience. And let's say that this one's reading a B. Then if I want to solve the problem of going from P to Q, which is precisely A sub PQ, then one way of doing it, there could be other ways, but one way of doing it is to take this route right here, which involves reading an A, which means that we're going to produce an A in the grammar, because reading in the PDA and producing in the grammar are one-to-one. Then, however I get from R to S by induction with the same stack height, and we know how to do that, which is A, R, comma, S. And then S to Q, what do we read on that transition, which is a B? Okay, so this works because either we have two mountains or we have one, or two or more mountains or we have one. If we have two mountains, then we just resort to making rules like this, or we resort to a rule like this. We're making all possible rules of this form. But we resort to applying a rule like this. And if we have one mountain, we must have this beginning because we ensured that the PDA must have every transition changing the stack height by 1 every single time. Okay, so let's do a quick example of this. Okay, so let's do this one. Actually, I'll do the one that we did here. So let's copy this big boy down to here. So we need to, oops. So here's an example. And we need to ensure that every transition pushes or pops, but not both. This one fails. So the way to fix this, spoiler alert, is to have it broken up into two transitions. Let's call this state Q3, and then this one is Q4. So what I'm going to do is I'm going to push on a 0, and then this one I'm going to pop a 0. Oops. So by doing this, I'm effectively doing what the original transition did, which was do nothing to the stack. Here it's pushing something on, popping it back off. And so we get the right behavior here. Okay, and then we also need to have self loops on the single final state where we pop every single symbol off the stack. So we have epsilon, $ goes to epsilon, and epsilon 0 epsilon here. So this is just ensuring that the stack can now actually be emptied. Okay, so what are some rules that we'll be making? Well, the first one that we saw was the A sub PP going to epsilon, where we had the same state in both places. So that's A sub, pick a state, any one that you want, and it's the same one in both places. So let's say Q1 I pick. So Q1 comma Q1, so the same state going to epsilon. So then we could have, let's say, Q3 making epsilon, and etc. So I'm not going to do all of them because there's actually quite a lot of rules that we'll be making. The second one that we saw was we needed the three states, one P, Q, and R. And then the way we handle this is we pick two states at the beginning. So just pick any two states. It doesn't matter. They could be both the same. So let's say I pick 2 and 3 just as an example. So Q2, Q3, making, in this particular case, no, they're not required because you can actually show that the PDA will end empty, but just purely from an algorithmic point of view, you want to ensure that the stack can actually be empty for absolute certain. So I want to make this so that this works regardless of the PDA that you are working with. Okay, so 2 and 3. So I got to have two variables of the form A here. The first one has to match so this one right here, so the first one of the left variable on this side has to be exactly the same as this subscript. And the second one on the end of the second one has to be the same as this one because it's representing where I'm going from and where I'm going to. Oh, that went too far off screen. Let me move that. So then what goes in the middle, you can pick any state that you want as long as they're the same in both cases. So let's say I pick Q0 in both cases. Okay, so that would be one rule that you can make. And you can pick any triplet of three states that you want. They can be the same or different. It does not matter at all. So in this case, this variable is actually completely useless. It won't actually generate anything, and that's okay. Why? Because there's no path from Q2 to Q3. So going from 2 to 3 is just impossible. And in fact, going from 2 to 0 is impossible too, so this variable is also useless. So you could actually make the grammar significantly simpler by eliminating all variables that are just useless, but I want to make this work for every single possible PDA. So I don't want to, in advance, delete variables or anything like that. Okay, so then now we got to pick a pair of matching transitions, one that pushes something and one that pops something. In fact, there are other rules here that are also made. So let's pick, you can pick any ones that you want. So let's say this one right here, the self loop on Q1, and the self loop on Q2 right here. So here's how I do this. So what I do is I recreate the transition, and if it's a self loop, I stretch it out to where the two endpoints are the same. So then I have Q2 go into Q2 here. And then the push one was 0, epsilon goes to 0. And then the pop one was 1, comma 0 goes to epsilon. So the recipe tells us that we want to go from this state on the left to this state on the far right. So I want to go from Q1 to Q2. And then what do? One way to do it is read whatever is on this transition right here, which is a 0. So 0. However, I get from this state right here to this one, which happens to be 1 and 2. So A, Q1, Q2. And then take this transition out, which is reading A1. And you can actually see the 0 to the n, 1 to the n behavior in here. And actually what will happen is this is at the bottom of the mountain, and the top of the mountain is going to converge on this Q3 state. So this Q3 state is actually pretty important for a reason. And let's actually do that example. So let's look at this transition and this one, even though they don't read anything. So I'm gonna again recreate the transition. So Q1 going to Q3, which in that transition was epsilon. Epsilon goes to 0 when we push the 0 on, and then Q3 going to Q2, which was epsilon popping the 0. So these were the two transitions that we added to make sure that the PDA works. So again, the recipe says, I want to go from this state on the left to this state on the far right. And that was AQ1, comma Q2. And what do we read on this transition? Well, it says nothing. So we put nothing there. How do I get from this state to this one? Well, from Q3 to Q3. So 3 to 3. And nothing read on this transition, which is, I'm not going to put anything here either because it's epsilon. So we can actually see the going up the mountain, so to speak, here. So this is at the bottom of the mountain. We generate zeros and ones. We keep doing this over and over and over until we get to here where we're going to apply a unit rule to make this variable. And the first type of rules that we had where they made epsilon when it's the same state in both cases, this will generate epsilon. And so because of that, this rule will produce epsilon. So in effect, it is a long way of having this variable make epsilon also. Okay, so that shows that every single PDA can be converted into a context-free grammar. Why? Because every PDA can be converted into this form where it has one final state, does this with the stack, and the stack to be empty. And the base case is just looking at all the states of the PDA and just making one of these rules for each. This one is just looking at all triplets of states in the PDA, again, which is easy to do. And then this one, all you need to do, where is it? So for this one, all that you do is just you look at a pair of matching transitions, which must exist, by the way. Actually, assuming that there is at least one transition, which you can assume that there is. As long as there's at least one transition, there is something like this. And so there is a pair of matching transitions. And so therefore, what you can do is exactly this. You can make a rule for this. And so you can convert it into an equivalent grammar because this is simulating the bottom of the mountain. And by induction, you meet at the right point at the top of the mountain if and only if P and Q are at the same stack height. Because if they were mismatched, so this is a question that was asked on Discord earlier today, if they were mismatched, say P and Q are mismatched, then by induction at some point they're not going to coincide with each other. And so therefore, the variable which is the same state going to the same state will have to produce something that is not empty and can never use the empty rule. And so that obviously will not work. Okay, so that's it for this conversion. I'm going to take another break and we'll come back into showing that some languages are not context-free. Jake asks, how long do you stream for Easy Theory? I do not know until I'm done. So depending on interest, I may do one more thing than the pumping lemma, but I'm going to do at least that. So I'm going to take like a 10-minute break or so, and we will be back with more context-free language stuff. So I'll see you then. All right, so let's get back into the swing of things. So I'm going to ask everyone who's watching, do you want me to cover deterministic context-free languages? Because I can. I'll do it based on user interest. I was planning on doing just the pumping lemma, but I realized that sometimes I teach deterministic context-free languages, and it might be of interest to some of you. And I may cover it in the advanced theory series, or just make a standalone video and not include it here. So whatever your choice is. And it would only be a cursory look at deterministic context-free. Yeah, it would only be based off of that. It wouldn't be anything too deep into it. All right, so let's continue. So now we want to see, okay, well, we have these two models that are equivalent. Are there things that are not context-free? So if let's actually try to think about this. So the reason why we were able to show some languages weren't regular is we looked at some strings that are in the regular language, and we could infer other strings that are also in the regular language. Not deterministic context-free grammars, so I don't really know much about those. It would only be deterministic PDAs, but the model is pretty much similar. Okay, so the question we want to answer is, so given W in L, which is a context-free language, what other W prime are also in L? So if I have a certain string in the context-free language, could we infer anything else? So it turns out that we can. So the way that I want to present this is, and I like a few days ago just did a video on this topic that I'm going to do. So I'm not going to show all the motivation for it, but I'm just going to jump to the punchline, so to speak. So let's look at so let's let G be a context-free grammar in Chomsky normal form for L, for this language L. Then what we can actually use is something called a parse tree. So a parse tree is equivalent to a leftmost derivation, which, remember, we can always assume that there is a leftmost derivation. So just as an example, so if we have that grammar, the famous grammar 0s1 or empty, then if we want to generate a string, we can apply rules like this. So something like this. But we can also think of it in terms of a top-down approach and try to visualize what the rule is actually doing. So what we do is we make a little tree here which grows downward. I don't know why computer scientists like trees that go down, but either way. So here, what's going to happen is whenever we apply a rule like this, the children of the node are going to be what the variable is replaced with. So this s at the top is replaced with 0, s, and 1, like this. And then what happens is the 0 and 1 are terminals, so there's nothing below them. They have no children. They're childless. But then this s got replaced with another 0s1. So 0s1. Okay. So then, yeah, so that's what happens. And then this final s got replaced with empty string. So I'm going to replace, have its child be the empty string. So if we read the leaves from left to right here, so we're reading the leaves, which are the things with no children. reading the leaves left to right. And what will happen is you will generate the string that you did in the derivation over here, because you see 0, 0, nothing, 1, 1. So from left to right. Okay, so it turns out that you can that these are equivalent to each other, because if you have the parse tree, what you can do is start from the top, figure out which rule was generated there, and then for any variable with children underneath it, you just look at the rules that it generated, and because it's a context-free grammar, you can reproduce the derivation. And similarly, if you have a derivation, a leftmost derivation, what you can do is just proceed by making the tree one level at a time, so to speak, by starting at the top, seeing what the variable was replaced with, and make those children, and then just keep going down. Okay, so parse trees and leftmost derivations are equivalent to each other. So why do we want to introduce parse trees? Because they're equivalent to leftmost derivations. It just makes the following argument a little easier. So why did I use a grammar in CNF? Well, this grammar wasn't in CNF, but why do I assume that G is a grammar in CNF? Well, we can always assume the grammar's in CNF because every grammar can be converted into one. So if it isn't in CNF, you just convert it. But suppose it is in CNF, then what? So the question we want to answer is, what do the parse trees for G look like? Because remember, in any context-free grammar, the right-hand side could be technically anything, right? But if the grammar is in CNF, now it has a certain structure. So the punchline of all this build-up is the parse tree is a binary tree. So this tree is a binary tree with the start variable up top, of course. And all of the internal nodes are going to be variables. So all the internal nodes, so all internal nodes are variables. And here's what the structure is. So a variable somewhere in the middle is going to, let's say A, is going to have two children, B and C, because the one type of rule says that we have one variable making two children, two variables. And also, what happens near the bottom is that if we have a variable, say A down here, then it's going to be replaced with a single terminal eventually, assuming the string is not empty to start with. Assuming the string is not empty, then the variable is going to be replaced with exactly one terminal like this. And so this is the structure of a grammar in CNF for its parse trees. So it's going to be a binary tree, meaning every single node has two or fewer children. The ones, for the most part, in the middle are going to be variables with exactly two children. And the ones down here, the variable is going to have one child, and the ones with the terminal have no children. So that's the structure of a parse tree for a grammar in CNF. Why does this matter? So let's think about getting from the top to the bottom. So if I follow some route that goes from the top to the bottom like this, then I'm going to see, for the most part, variables along the way. So I see variable, 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 until I get to this very last, second to last point. Then I'm going to see a terminal, and then that's it. So what we can do is, if I make the tree super, super big in terms of height, make it really, really tall, and as long as the grammar doesn't change, then as long as I make the tree tall, then I'm going to repeat variables along the way. And that's where the repetition part comes into play. So, and the way that we make the tree taller is if we make the string that it generates longer. Because at a certain point, if I make the string a little longer, the tree has to grow taller, no matter what. Because there's only a certain number of nodes I can even fit in here because it's a binary tree. Okay, so if we make the string W, so I should say that this part is W. If we make W longer, the tree eventually, at least, eventually, must grow taller. Okay, so they must grow taller. So how do we actually use this to our advantage? Well, because a variable now must repeat if the string is long enough, then we can do some repetitions. So let's actually analyze this a little further. So here's our tree again, now in blue color. So let's say that we have a variable a somewhere in the middle, and we go from the top to the bottom like this. And let's say that a is a variable that repeats. So there may be others, but let's say that a is a variable that repeats, and I'm going to use a different color because I can't see this. All right, so I'm going to use white for the variable a. So let's say a repeats here. And because a is not the start variable, because one, the start variable can't repeat, and I guess that's enough to show. So a is not a start variable, so it must make something of the string. It must make a non-empty portion of the string. So the top one is going to make some part of the string, maybe all of it, maybe none of it. Actually, it can't make all of it, but it could make most of it. And then the bottom one is going to make something of the string. So I'm going to give these names. So this part I'm going to call U. I call you maybe. This part I'm going to call V. This part is going to be X. This part's going to be Y. And this part's going to be Z. Okay, so what we can see here by this logic is that A can both make X, because that's what this little subtree can make, and this top A could make the whole thing VXY. So A could also make VXY, because that's what this top occurrence of A makes. But it can also, if we think about this a little more, it's not just VXY, it's VAY, because this top occurrence of A, because it's the same variable, makes the V part. Then whatever A makes, again, because it's the same variable, and then the Y part. And what you can see is that by the end of, once the dust settles, you can have A making, so this star means in one or more rules, I guess. Actually, I'm going to use a different notation. Yeah, so A eventually will make V to the I, X, Y to the I for any I at least 0. So for any choice of I that you want, you can repeat the V and the Y part as many times as you like, and finally finish off with the X. So we have the V and the Y part in equal numbers, so to speak. Okay, so then for the whole tree, what we can see is that the start variable can make the U part, so the U part, as well as what the A part can make. So because it's the U part followed by whatever A can make, which is, we just determined is this. So V to the I, X, Y to the I, and then the final Z way over here. So it can make this string. And so this tells us that this string that we just made is in the language because we just made a grammar for it. We made a parse tree for it for all I at least 0. Which is kind of similar to the one that we saw for regular languages, where we only had 3 pieces, but now we have 5. And we have 2 pumped pieces. So V and Y are both pumped pieces. Okay, so what do we actually do here? So what we can do to get some other conditions is we look at some of the additional things that can happen. So the worst possible thing that can happen in terms of this right here is that the variable A and the second occurrence of it is right beneath the first occurrence. It's right beneath it. And of course, there might be some other variable over here. But here's the key. It doesn't actually look like that. It more looks like this. So it looks like this instead. So these two trees are disjoint from each other. Why? Because it's a context-free grammar, and you can only replace one variable. You can't replace two things with stuff. So here, we actually have disjoint trees right here. But notice what happens. So this part of the tree is the y part, right? So remember that that this part right here is the x part, and the part on the right side after the x is the y part. So whatever happened to the v part is what the top A made that the second A did not make, but they coincide on this part right here. So if we actually look up here, there's like a gap in between, whereas down here it could be that there is no gap there. But because of this other variable over here, this side must have some characters in it because b is not the start variable. So what this tells us is that that y, if v is empty, then y is not empty. And we can also flip this around to say, what if the a variable was on this side and the b was on the left side? Then the y part's empty, but that forces the v part to be not empty. So in either case, one of the two of v and y is not empty. And it kind of makes sense why that's the case. If both v and y were empty, then putting more v's and y's into the string, like doing here, is not going to change the string, so that's not going to tell you anything interesting. So what we have is that v and y together have at least one character in total. They might both be non-empty, I don't know, but one of them has to be non-empty because of this property right here. Okay, but what else can happen? If you remember from the regular pumping lemma, there was one thing that was not actually needed, but it turns out to be really useful, which was that the beginning of the string was at most p characters, with the x and y part. Hey PokeFan Games, I just noticed that you're here. Welcome for joining. So, what can happen? So, let's look at this parse tree again, top from the bottom, and we have two occurrences of A. But what I'm going to do here is I'm going to pick the furthest down occurrences of A. So, so these right here are the furthest repeats down the tree. Do v and y don't generally have the same value? Yeah, they could be totally different, and we'll see this in a proof coming up. That they could be totally different. Yep, absolutely. But they could have the same value, but there's no condition on whether they're the same or not. Okay, so let's say that these are the furthest ones down. Then what will happen is that if you think about it, if the length of the string that we're generating in total is way, way, way bigger than p characters. So let's say that this has way, way more than p characters. Then what we can do is we can actually look at this part right here, which is this, and assume that this has less than or equal to p characters. Why? Because the same argument applies if we have exactly p characters. So if the A's were as far up as possible, even though the furthest one's down, they're still really, really far away, then what we can ensure is because of this, because of making the tree taller, we can ensure that the number required to repeat here has that this part of the tree, the big occurrence of A, the part that it makes is at most P characters. Or the P here is the amount that is needed to ensure that there is a repetition. Okay, so even if these two occurrences of A are pretty far away, as long as they're the furthest ones down, we can guarantee that what is generated there is less than or equal to P characters, which is the threshold to cause a repetition. If it was exactly equal to P, we can guarantee that there is. But it could be that they're really, really close to the bottom, in which case they could be way less than P characters. But it can't necessarily be more because they're the furthest ones down. Okay, so what this all amounts to is something that you're not going to like hearing, but it's something called the pumping lemma for context-free languages. And what is the statement? It is let L be a CFL. Then there exists a pumping constant, P for this language L, and for all strings W in L with the length of W being at least P. So this is saying that there is a parse tree. The W being in L shows that there is a parse tree. And then this one is ensuring that there is a repetition of variables from the top to the bottom. Then what we have is something similar to the regular pumping lemma one. Then there exists a decomposition of W into those 5 pieces, into U, V, X, Y, and Z, such that those 3 conditions occur, which are that U, V to the I, X, Y to the I, Z is in L for all I at least 0. This is because we can analyze the repeated variable, and we can basically repeat sub-parse trees, the inner parse tree that corresponds to both occurrences of that one variable. You can see how to do it geometrically. You take the bigger A parse tree and copy and paste it down to the lower one. Or you take the lower one and copy and paste it up to the top one. And that'll actually show it here more clearly. I invite you to actually do that yourself, but I'm not going to do that here. And then we have the other 2 conditions where Vy is at least 1 character, and the length of Vxy whole thing is at most P. Because we can look at the lowest 2 occurrences of those variables, of the repeated variable. Okay, so things to mention here is that this right here is not necessarily the beginning of the string, right? Because in the regular case, we had the 2 beginning pieces had at most P characters, but here is the 3 middle pieces. So it could be that the pumped pieces, the V and the Y part, could be anywhere in the string at all. Okay, so we just got to be cognizant of that when we're doing proofs here. Okay, so what I want to show here is an example of showing that a language is not context-free. So for those of you who are watching, there's a video coming out tomorrow that's 40, let me check. It's a really, really long video. It's 49 minutes long tomorrow, which is going to go over 4 pumping lemma for context-free language proofs tomorrow. And this is one of them, but I might as well do it now anyway, just in case people watch this video and not that video. So, in effect, this proof will carry very well over to proving other languages to be not context-free. So even though it's like the prototypical language is actually really, it carries very well to other languages, unlike 0 to the n, 1 to the n. So this one is 0 to the n, 1 to the n, 2 to the n. So it's where 3 pieces have the same number. So the 3 different characters here is actually really, really important. Because if I restrict to only 2, then you can show that this is context-free pretty easily. But it's 3 pieces that really matter. Okay, so how do we do this? So I'm going to call this language L. So let's suppose that L is a CFL. Then, of course, there exists a pumping constant P for that language. All right, so then what do? Well, now we gotta pick a string that's in the language and at least P characters. So I go over the reasons why to not pick other strings in the video that's coming out tomorrow, but I'm going to just tell you that you should choose W to B, 0 to the P, 1 to the P, 2 to the P. So watch the video tomorrow if you want to see why you shouldn't pick some other string for this. Okay, so what do we do here? Well, now we got to look at every possible decomposition into those 5 pieces. Why? Because if I leave one of them out, that could be the one that allows us to stay in the language no matter what. So we got to look at all decompositions. Decomps into U, V, X, Y, Z. According to the rules, of course, just like before. Well, the thing is, well, the V and the Y pieces, those are the pieces we're going to put more of or take away from the string. So let's actually think about it. So if the V and the Y are only in the zeros, so the way to handle these is to look at a bunch of different cases. So case 1, I'm going to say is V and Y are only in the zeros. And then we'll have a case of 1 and a case of 2, and then we'll carry on from there. So V and Y are only in the zeros. Then if we put an additional copy of V and Y in, that means that we're going to put more zeros into the string. And because they're not touching the 1s or the 2s, the number of 1s and 2s are going to stay the same. So if we pump up the jam to I equal to 2, then this will cause the number of zeros to be strictly bigger than the number of 1s, let's say. And then that's enough to show that it's not in the language anymore. Because to be in the language, you have to have exactly the same number. And the number of zeros is bigger than the number of 1s. And that's enough. And in fact, for case 2 and 3 at the same time, where V and Y are only in the 1s or only in the 2s. Then if we do the exact same thing, if we pump up to I equal to 2, then that will cause either the number of zeros to be strictly less than the number of 1s, or the number of zeros to be strictly less than the number of 2s. In either case, we leave the language. So here we have either the number of zeros being strictly less than the number of 1s, or the number of zeros to be strictly less than the number of 2s. In either case, we'll leave the language here. Okay, so you may think that's all the possible cases, but there are other cases. So one could be that V and Y have some zeros and some 1s in them. It could straddle this boundary between the two. So let's say case 3, case 4, I should learn to count. V and Y have zeros and 1s. And note here, if they have zeros and 1s, they can't possibly have 2s. So if we do the same thing, we pump up to I equal to 2, then either the number of 2s will be strictly less than the number of 1s, or the other way around, number of 2's being less than the number of 0's. And I'm not going to do this case, this last one, where v and y have 1's and 2's, because it's very similar. The number of 0's in this case doesn't change, but the number of 1's and 2's both do. They go up. And so, so then we break the condition that we're in the language. The only other possible case is then, well, v and y could have 0's, 1's, and 2's. But this is where the vxy condition actually applies. So the vxy condition, being length less than p, says the v and the y part are within p characters of each other. And so if they touch the 0's and the 1's, they have to go all the way across this section of 1's right here and to hit the 2's. But that whole section of 1's has p characters in them. And so that's impossible. So it's impossible for v and y to have 0's, 1's, and 2's simultaneously. And because of that, that shows us that we can actually, we've handled all possible cases, because it's either in one section or is in 2 adjacent sections. It can't be in all 3 sections. And so because of that, we looked at all sections, we pumped out of the language in every single case, and so this tells us that L is not a CFL. Okay, and in fact, this is the only pumping lemma proof I'm going to do here because, well, I got 4 of them coming out tomorrow, and second of all, this proof actually carries very well to other pumping lemma proofs. My prof made half my midterm pumping lemma proofs, almost cried. Yeah. We don't like seeing our students cry, but we gotta make sure that you know how to prove stuff, because that's part of being a computer scientist. And this class is kind of like applied mathematics in some sense. So you gotta be able to prove stuff. Okay, so this is the only pumping lemma proof I'm gonna do, but so make sure to watch the video in its entirety tomorrow. Get that sweet, sweet ad revenue. No, I'm kidding. Okay, so I want to show you one more thing before we conclude for today. So I'm not going to do deterministic context-free languages because I'm going to save it to the advanced series. All right, because at the institution I'm at right now, we don't teach deterministic context-free. So, yeah. Okay, so what I want to do here is to show that the CFLs are not closed under intersection or complement. Okay, so let's handle intersection first. So if I find 2 context-free languages whose intersection is a not context-free language, then that's all that we need. So if we take these 2 languages, which are A to the N, B to the N, C to the K, where N and K are at least 0. So A's and B's being the same, and C's can be whatever it wants to be. And then the second one being A to the K, B to the N, C to the N. So the B's and C's are the same. And in fact, in tomorrow's video, I'm going to give you a completely different proof other than this one to show not closure under intersection. So we can clearly see, or hopefully clearly see, that L1 intersection L2 is A to the N, B to the N, C to the N, where N is at least 0. Because this is saying that in the intersection, we got to have the same number of A's and B's and the same number of B's and C's. And so they must all be the same by that logic. And so how do you actually make a context-free grammar for each one of these? Then, so I'm going to do L1. I'm not going to do L2 because it's extremely similar. So for L1 grammar, so let's just make sure that the a to the n, b to the n part, we can do that pretty easily because that's like 0 to the n, 1 to the n. So I'm going to have s going to a, s, b, or empty. So that's the a to the n, b to the n part. Then what I'm going to have here is a variable s0, which is the start variable, which is going to concatenate whatever the a to the n, b to the n part is with any number of c's at all. So I'm going to have it be s, which is the a to the n, b to the n part, along with a variable I'm going to call c, where c is going to generate any number of little c's that it likes. So c is going to make little c, big C, or empty. So this is just a little grammar, little piece to say any number of c's that you want. So a to the n, b to the n, followed by any number of c's that you want. And this, and the grammar for L2 is extremely similar. So because their intersection of these two languages is a not context-free language, that tells us that context-free languages are not closed in their intersection because I can make a grammar for these two languages. And then that shows that they're context-free and their intersection is not context-free, which is all that we need. Okay, so there are actually two ways to prove complement. So I'll show you the easy way and the less easy way. So the easier way is to use De Morgan's laws, which is to say that L1 intersection L2 is the same thing as saying L1 complement union L2 complement, and then the whole thing complement. So it's a proof by contradiction here. So if context-free languages were closed under complement, if they were, then L1 complement would be context-free because it's closed under it. L2 complement is also context-free, so it's closed. The union of two context-free languages is context-free. We've already seen that earlier today. And then, so the stuff on the inside is all context-free. And then this final complement, assuming it's closed under complement, means that the final result is a context-free language. But if we substitute these two languages right here, we get something that is not context-free on the other side. So that shows us that there's at least one example of two languages whose, because their intersection is not context-free, they cannot be closed under complement because you result in an intersection. This is which is not context-free. This actually tells you something interesting, that one of the three following statements is true. Either this language is not context-free, complement, if the complement of this thing is not context-free, or the complement of this thing is not context-free, or the union of their complements is not context-free. One of those three must occur. And all three might be true, but at least one of them is true. But I want to do a constructive proof. So I want to do something called a constructive proof, which means that this tells us that there exist languages whose complements are not context-free. But here I want to give you an explicit example of a language who is context-free, but its complement isn't. And the easy choice is, or at least to choose it, maybe it's not correct. The language is the complement of a to the n, b to the n, c to the n, with n at least 0. The complement of this thing. So I have to be able to convince you that this complement language is context-free. So let's try to do that. So I'm gonna copy this guy down here so I have some room because it's gonna take some space. So I want to convince you that this is a CFL. So you gotta think, what strings are in the complement of this language? So all strings that have that are not of the form A's followed by B's followed by C's and have the same number of each. So what are the possible things that can go wrong? Well, if the string, so let's see. So let's say that W is in L if, what are the possible things? So it could be that W contains BA. So if it has a BA in it, it can't be in the original language. It must be in the complement one because the original one has no BAs in it at all. Similarly, if it has CB or CA. So if it has any one of those three substrings, then it's in the complement. And to represent all strings that fit this pattern, this is actually regular. Because it's all, you can actually even make a regex with it, like sigma star, BA, sigma star, the whole thing union, sigma star CB, sigma star union, sigma star CA, sigma star. And that's a way to represent all strings that have this property. So then now, if it's not one of these three, it must be A's followed by B's followed by C's, but the counts must be off. That's all that can go wrong. So W is of the form A to the I, B to the J, C to the K, where I is not equal to J, or I is not equal to K, or J is not equal to K. One of those three must happen if we have a string that is of this form, but also in the complement language. So I'm only going to do one of these two. So, sorry, one of these three, because the other ones are extremely similar. So let's do this one. Let's do this one. So I want to make a grammar for, so CFG for this language. So A to the I, B to the J, C to the K, where I is not equal to J. Okay, so K could be anything. It's just I and J are not the same. Okay, so what do we actually do here? So the thing to note about not equal is it's in one of two possible camps. It's either I less than J or I bigger than J. And so what do? We just do union of those two cases. So here's what we do. So I'm going to have it be the start variable. So this is the start variable. Is going to make, this is going to be made by one variable. I'm going to call A. So A is going to make this piece. In fact, I'm going to change the color to match here. So I'm going to make this red. So that A is also red. And I'm going to make this piece yellow. And I'm going to make the corresponding variable of yellow. So then, so this piece is going to correspond to the A's and B's made here. But the C's could be anything that it wants to be, any number of C's that you want. So we're going to do the same trick that we did before where we have this variable C that just makes a bunch of C's at the outset. So C is just going to make a bunch of C's. No problem at all. Okay, so then what about this one? Well, I'm going to have or, then we'll have B, which is the part that's going to make the I bigger than J piece, and C afterward, because again, whichever of these two is the case, we can have any number of C's afterward. So then what is the A variable going to do? The A variable, if there are more B's than A's, it's going to make A's and B's in tandem, but at least one more B after it. So it's going to have, it's going to be A, capital A, little b, so make them in tandem. But also it's going to make at least one more B, but potentially more B's. So I'm going to have little b, at least one, and then I'm going to have another variable to just make more B's if necessary, because it's not necessarily just one more b. It could be at least one more b, any number more. So I'm going to have a variable called a sub b, and a sub b is just going to make more b's. So the purpose of this variable is just to spit off b's, just like the c variable spit off c's. And then what about the other case? The other case is where we have a bunch of a's here. We have more a's than b's because I is bigger than j. So the b variable, which is responsible for doing this, is going to make something similar. So a's matching with b's, but then it's got to produce an a. So now what we actually do is we actually we need to produce another a here at least. But we need to produce it in a different way than what we did here. So the b's in this substring are at the end of the AB lick right here. The a's are at the beginning. So we need to, instead of having it like this, we need to have the variable on the front. So we need to have b sub a, which is going to spit off more a's, and then the a at the end, not the beginning. So then the b sub a variable is going to make a whole bunch of a's. Okay, so that was actually kind of a complicated grammar. Actually, what I should do is I'm going to change the name of these. Yeah, I didn't like the subscript because it kind of looks like the rule above them. So I'm going to have them be x and y. So x down here, and then y down here. And so this is a grammar, although not too simple. The key here is to notice that when you have not equal, it's the same thing as saying less than or greater than. And then you just do the union of the two cases. Okay, so then to get back to this, each one of these is a context-free language. All the strings that have this form or this one or this one. So if we have three context-free languages and take their union, the result is context-free. We showed that before. If you take the union of CFLs, you will get a CFL. And here we got a bunch of, in fact, 3 regular languages. And if you union regular languages with context-free, you still get context-free because every regular language is context-free. And so when you union these in, you're essentially just unioning context-free languages. So you get a whole string of context-free languages with union, and therefore the whole result is context-free. And so therefore, because it's the union of a bunch of context-free languages, this language therefore must be context-free, the complement of this thing. So if we think about where we currently are in the world, we talked about finite languages, kinda, not really, but it's languages that have a finite number of strings, and every finite language is regular. So examples of a finite language are like the empty set as an example. An example of a regular language that isn't finite is like, say, sigma star or a star or something. And then now we have context-free languages, which, because every regular language is context-free, we get this bigger bubble. So context-free. And an example of a context-free language that isn't regular is, for example, a to the n, b to the n, where n is at least 0. And another example is balanced parentheses. Okay, and now we just stepped out to the big, wide, wonderful world, and we found some examples of languages that aren't context-free. So like a to the n, b to the n, c to the n, where n is at least 0. And an example of one related to that that is context-free is the complement of it. So a to the n, b to the n, c to the n, where n is at least 0, and then the whole thing complemented. Cool. So that's all I wanted to do in this live stream. So thank you very much for watching and sticking to the end, everyone who's watching. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. As I've said before, I'm starting tutoring, one-on-one tutoring services. So if you want to do that, head over to the Discord server. I have details on how to actually schedule for that. And again, thank you all for your support. I will see you next week when we're going to talk about the next stuff, which are Turing machines and